Did it start?
So yeah, I have started it.
Okay.
I've started very okay. Hello everyone, and welcome to IEEE Women in Engineering Albuquerque section public talk series. For today's speaker, we have Dr. Amanda Bienz, an assistant professor in the computer science department of the University of New Mexico. She has obtained her PhD from the University of Illinois at Urbana-Champaign, and her research focus is on high-performance computing and scientific computing with the aim of improving the performance of parallel applications. In today's talk, she will be discussing super algorithms for supercomputers, and it will be a 1-hour talk with 45 minutes talk and 15 minutes question and answer session at the end. So let's welcome our speaker, Dr. Amanda Bienz.
Thank you so much, and thank you for having me. So yes, I'm going to talk about super algorithms for supercomputers and also just a bit about my experience with how I got into this area. So let me see if I can, okay. So a little bit about me. I actually decided that I wanted to be a computer scientist way back in 4th grade. And I know when you're a little bit older, it's hard to picture what a 4th grader looks like. So I included a picture of me from 4th grade here. It's very odd, but I had a very great, some great role models growing up. So my aunt, who I was very close to, was actually a computer scientist as well. I'm sorry, 1 second, my mouse is not working. Okay. So growing up, my aunt was a computer scientist, and she really influenced a lot of that decision. But also, I remember in early elementary school sitting with my mom at our old computers that were running slowly with a series of floppy disks and going through and removing everything with the floppy disks, and then having like 20 floppy disks we had to use to reinstall Windows 93 or whatever it was. And so I decided very early on that I wanted to go into computer science. And then I was actually fortunate enough that my high school taught some computer science classes. So I was able to take them in high school. And actually we had a female teacher for that as well. So I actually had a lot of experience with female computer scientists growing up. So I went to undergrad at a school called Elon University. This is in North Carolina. It's a liberal arts college. And I put the pictures of the 3 computer science faculty who were there while I was a student. I had absolutely wonderful professors there. And actually, this does not include a 4th faculty who was there because she was in databases and it was more computer information sciences. But if you counted the 4 of them, we had 50% female faculty, which was also pretty unheard of. And so I was the only woman in my year for computer science students, but I think there were only something like 7 or 8 students who graduated in my year. I do know the department has changed a lot. If you look at their website now, they have a lot of faculty because every computer science is growing everywhere. But I had a really wonderful undergrad experience there. And so I went to undergrad assuming that I would get a degree and go and get a job. Nobody in my family had gotten an advanced degree, so I never really thought about it. And about halfway through undergrad, I took a class on operating systems and architecture that I really enjoyed. And I talked to one of the professors there about taking some more advanced classes, and he got me to do some of the research experience for undergraduates. So if anyone watching this is an undergraduate and you haven't done research, but you're interested in it, I highly recommend checking out. They're called REU programs, or research experience for undergraduates. They're at different universities over the summers. And so I spent 2 summers doing research at Clemson and then DePaul. And so I was able to get my hands in some research that was actually used then when we published some papers. So that's kind of when I considered going forward and doing research. I was a computer science major and then added on a math major as well because I had to take extra credits and the math classes sounded like the most fun to me. So I ended up deciding to go to grad school. And so I went to University of Illinois for grad school. And I got my PhD in an area called scientific computing, which is essentially doing numerical analysis or solving sparse matrix problems on high performance computers or supercomputers. So I was really able to combine my math and computer science backgrounds there. So I worked closely with Luke Olson and Bill Gropp, who are images there. I'm with my advisor, Luke Olson, in our funny outfits when I graduated. And so most of my research really started at Illinois. And I just wanted to talk a little bit about grad school in case anyone's considering going to grad school. UNM is an awesome place if you want to consider that. But also, if you go to grad school, especially for underrepresented groups, I highly recommend applying to fellowships. So I was actually able to start at Illinois with the NSF fellowship. And because of that, I kind of got to choose my own research directions, which was really nice. And then I also got to be a part of something called the NSF Grow. And this is essentially an internship program that I got to go work at in RIA in Paris for 4 months and work with some researchers there on my research. And these images are what my bike ride looked like every day. So I got to pass the Eiffel Tower one way and Notre Dame the other. So if you're able to go to grad, or if you go to grad school, I highly recommend looking at fellowships because these types of opportunities do come up. And they're really, I can't imagine another time that I'm going to have an opportunity like that. The other thing, if you're considering going to grad school, is that conferences are a really, really wonderful part of grad school. And they were one of my favorite parts. You really have opportunities to go travel and see some unique places. And so I was able to go to really a bunch of different countries. Barcelona was very neat. I was able to go to Germany and see the Christmas markets. We have conferences in Lake City or Taos or Copper Mountain, ski conferences. So if you are going to grad school, highly recommend checking out just general conferences. But there are also a lot of conferences that are aimed for women. I never had an opportunity to go to Grace Hopper, but I'm sure most of you have heard of that, and it's a great conference. The one I did have an opportunity to go to that I really recommend is called Rising Stars. So if you're getting near the end of your PhD program or you're in a postdoc and you're considering becoming a faculty member, there are conferences that are called Rising Stars. There's one in EECS, Electrical Engineering, Computer Science. The one this image is from is Computational and Data Science. They have these in a bunch of different areas, but it's for women who are wanting to become faculty or thinking about becoming faculty. And some of them, so this one, they had people from national labs there, people from industry, and they talked about all the different jobs and work-life balance. And it was a really great conference. So for anyone who has not heard of that, I highly recommend looking into it. And this one in particular, when I went, it was in UT Austin, but I looked it up, and this past year, it was actually in Albuquerque and hosted by Sandia. So definitely something to keep in mind that it is sometimes in this area. Also, I just want to mention, if anyone has any questions, feel free to interrupt me at any time. And so now I'm an assistant professor here at UNM. I'm in the computer science department. I started in August 2020. So when I started, I did not see this building. We were at home for the first year and a half, I guess a year. But we are now back in person, which is really nice. And I'm getting to meet everyone here. So I'm working in a research group here on high performance computing, scientific computing, and I'm going to talk a little bit about some of the research that we look at. But a quick plug is that we are hiring. So we do have some tenure track positions right now in computer science coming up. And so I just want to say, in case anyone here doesn't know this about UNM, we are a minority serving institution. And actually in computer science, we are nearly 1/2 of our faculty are women, which is really unheard of. And then we collaborate really closely with the national labs. So if you're on the job market, if you know anyone on the job market, I really cannot speak highly enough about our department, and you should definitely check it out. Okay, so going a bit into what I look at in my research. If you saw that wave simulation that was on the first screen that I had up on the title page, this is a simulation that is just creating a very big wave. It goes to the boundary and then it bounces off and comes back. And so the image on the first screen just looked like a nice wave. But here we see that we actually have all these little black lines over it. This is a mesh that is over the problem. And so how we actually solve these types of simulations is we put this mesh over the problem, and then we evaluate each point or the wave at each point on the mesh at each time step. So you can see at the beginning, the wave is only in the beginning or the middle of that mesh, and then it slowly spreads out to all these other points on the mesh. So we are just calculating data at every point on the mesh. However, when we get to realistic simulations, they're going to be a lot larger than this and a lot more complex. And we end up having really large memory constraints. So we have this huge mesh that we're computing points on, and it's probably not going to fit in the memory of a single computer. And then we also see that it becomes very, very costly. And it's not that it will take a few minutes or a few hours to run. It might take days or weeks or months to run a simulation. They become very, very expensive. So my research looks at taking applications like this and getting them to run on something called supercomputers. So I'm sure many of you have never heard of a supercomputer before or don't know much about it. So this is a picture of a supercomputer. They're huge. They often have entire buildings built just to store a supercomputer. So this is an image of a computer called Blue Waters. It was at Illinois when I was in grad school. It no longer exists. But there's an entire huge building, and it is just full of this computer and the file system where you store all the data for this computer. And that's all that was in the building. So you can see there are quite a few rows of huge computer here. So it's a bit different than working on your personal laptop or a desktop. So we use these supercomputers to solve simulations so that, one, they'll fit, but also so that we can solve them in a reasonably fast time. So if we look a little bit at what a supercomputer looks like on the inside, we have a really large number of computer cores. So these are the actual processors where we can do our computation. And these cores are connected by links of a network. So it might look something like this, where you have 12 CPUs, and each of the CPUs are connected to just neighbors. They're not all connected to one another. They're connected to their neighbors. And so if we want to use a supercomputer to do our simulation, we typically would split our application across the cores, so that each core can compute a part of the mesh. And then we need to communicate between the cores. So we need to know data that's stored on other cores, and we have to send that data across the links. So if we look just back at that wave simulation, we have that mesh. If we wanted to solve this in parallel, we would split that mesh across all of our processes. So in this case, all 16 processes. And so each process now calculates their little square of the mesh. However, if you look at the calculations, say in the bottom left here, we're waiting for the wave to get there to have information to calculate. We get that wave information from our neighbor. And so we're waiting on the information to come from our neighbors to say, okay, the wave's here, now you can calculate the wave. And that's actually communication. So we're constantly sending data between these processes to tell them where the wave is and that it's coming to them, that they need to actually start computing stuff. That communication is really expensive. So when we look at parallel applications, the bottleneck is almost always the parallel communication, the talking between those cores. So the goal of my research is to reduce those communication costs in existing parallel applications. So we want to make these applications run faster, allow them to run on more cores, have bigger supercomputers that they can run on. And the only way to do that is to make the communication work better. So just to look a little bit at what kind of communication happens here, I've labeled these processes so they each have their own portion of the mesh. Certain processes are labeled P, Q, R, and S. When we're communicating data, we need to know what's called boundary data. So everything on the edge. So process S gets everything right above it. It also gets stuff to the top left and stuff to the top right. And that's all sent to it, along with sides and stuff from the bottom. So we have a bunch of data. All those processes are sending their data, some of their data, to process S. So in this case, we're sending some data to process S. We also could look at, if we just look at process Q, it will have to send data to multiple processes. So to T, S, and U here, along with processes to the side of it. So this is what communication is. We have to communicate those boundaries so that other processes have that information, and then they can go ahead and update their wave appropriately. So when I talked about communication, I talked about the supercomputer. I kind of lied when I said it's a bunch of CPUs or cores connected by links. It's actually a little bit more complicated than that. So if you think about your personal computer today, they're almost never going to have just one core. You likely, when you bought your computer, it said dual core or quad core. And so this means there are multiple processes on your CPU, multiple cores on your CPU. So the same thing happens with supercomputers. Instead of having a single core connected by links, we have something called a node that's connected by links. And if we look at the node actually has, it's kind of complicated. So this is what a node would look like. We have two sockets or CPUs often on the node. So on these sockets, we have the processing units. The processing units are the cores, what actually do things. So if I have 16 processing units, I can do 16 computations at one time. There's also, if you see, there's this main memory that is where all of our data for a program is stored. So as I'm running a program and I calculate a value on the mesh, I store that value into main memory. There's also these things called cache, and that is essentially another part of memory. It's going to be smaller, but also a lot faster. So we have some different levels of this hierarchy here that we could be communicating on cache, that if we have two processes, they're on the same socket and they want to send data to each other, their communication is on cache. Sorry, I still can't pull things up. Okay. And then if we have, my mouse is broken. Now I have something in the middle of my screen. Okay. There you go. If we have two cores on the same processing unit and they send data to each other, that data is sent through cache, it can be really, really fast. If we have two cores that are on different processes, they send data to each other, it can't go through cache because they don't actually share one cache. So it instead has to go through main memory. And then we also could send data between these nodes. And in that case, it goes across the links of the network. So there are these different types of communication, and applications typically don't take that into account. So often when an application is written, they say, I have to communicate with these other processes. I'll go ahead and do that. They don't pay attention to which node they're on. Is it communication that's going through cache, through main memory, or is it actually that expensive communication through the network? And so a lot of my work is taking the architecture and seeing where are we actually communicating? How expensive is it? And if we look at the different types of communication, this is on Blue Waters, that computer, supercomputer that there was an image of. If we look at how expensive that communication is, this shows, this plot shows the different costs based on where we're sending. So the purple line here is if we send between two processes that are on that same socket or CPU, they share cache. It's going to be pretty inexpensive to send data on socket. If we send on node, but between sockets where they don't share cache, that's the red line. It has to go through that main memory, which is slower than cache. And then the green and blue lines are sending through the network. So the green line is if we have less than 4 processes on a node, and the blue line is if we have 4 or more processes on the node, or the blue dots are for that. So we can see there are really large differences between sending on node and off node. And that's really what we pay attention to. We want to reduce how often we send between the nodes because it's very, very expensive. And so we rewrite algorithms to reduce how much goes between nodes. So if we go back to this example of the mesh where we have these processes, if we outline these rows of processes now saying they're nodes. So node 0 is that orange, it has the first 4 processes. Node 1 is the yellow, it has the second 4 processes. So process S is on node 1 here. We can see that for this example, process P, Q, and R all have to send to process S. So there are actually 3 messages here between the 2 nodes. Those are all 3 going to be very expensive messages. And then similarly, my process didn't get updated. Process Q has to send to the bottom 3 processes, S, T, and U. And so it sends to all of those processes as 3 different messages. Again, we have 3 messages going between those 2 nodes. That's very expensive. So we do something called locality-aware communication. That is just, we want to reduce those duplicate messages between the nodes. So instead of sending all of the data between all of our nodes, we say, here is all of the data that needs to go from node 0 to any process on node 1, and we gather it all on a local process. And so then we can send all of that data as a single message between the nodes, and then we have process Q redistribute that data across the node. So we can do all of the communication with 1 message between nodes. There's more messages within the node, but that's a lot cheaper, so that's okay. And so we do this type of aggregation, and we put this within existing parallel applications. So I'm not going to get into what algebraic multigrid is, but this is, or details of it, but in general, it's a solver. It's a way we solve numerical problems. And the green line here is the code base called Hyper. This is really a widely used code base from Lawrence Livermore that does algebraic multigrid. If you look at applications at some of the labs, a large number of them call Hyper. And so this graph is just showing the cost of solving a single problem with Hyper on different numbers of processes. So we start with 128 processes and we solve on that. Then we're saying, we see, can we get speed up if we instead distribute that mesh across 512 processes? So each one has less, and then 1,024 and so on. And so the green line is Hyper. The dark blue line is just our own implementation that's really the same as Hyper. It's doing everything the same as Hyper. We're getting all the same solutions. There are some slight differences, but it's really doing the same thing as Hyper. And then the dotted line is just using the aggregation that I talked about, and nothing else changes. So the only thing changes here is that for communication, we do that aggregation to reduce how much is going between those nodes. And we actually get nearly an order of magnitude speed up at times over Hyper. So this goes much, much faster than Hyper and our existing approach that doesn't do aggregation. And it also it's called scaling out to more processes. So you can see that on 8,000 processes, this improved method is cheaper than it is on 4,000 or 2,000 processes. And that's not the case for the standard or Hyper approaches. They actually, once we run on 512 processes, we can't run on more processes and have it get cheaper. So we actually could run on 512 processes. We can't use any more of the supercomputer, even though there might be 100,000 available for us. So a lot of my research looks at using this type of aggregation or similar methods to reduce that communication that's so expensive. And then, so that was all about blue waters, but newer computers today actually look quite a bit different. So if we look at the top computers today, they're all considered heterogeneous. So this means that there are GPUs on every node. And a GPU, in case you don't know, it's a graphical processing unit. And it basically, you can think of, if you have an image on your screen, there are a bunch of pixels. At every pixel in that image, some calculation is happening to change the pixels. So GPUs have been repurposed in recent years to do math. They're really good at doing parallelism because they can calculate many, many numbers at one time, which would be the same thing as updating all of those pixels. So the computers look more like this today, that this would be a node of a computer now. We have maybe 4 GPUs, and each of them are connected in some way. So GPU 0 and GPU 1 are connected here, and they're both connected to CPU 0. Because we have GPUs, all of the calculations are actually done on GPUs now instead of on the CPUs, because they can do calculations much more quickly. The problem is it's very expensive and difficult to communicate between the GPUs. So that communication that was already so expensive is now much, much more expensive than it was. And there are also a lot of different paths for how you do that communication. So if I wanted to communicate from GPU 0 here to another node, I could take this red dotted line, and that will take me over to the network, and then send across that link of the network over to the other node. Or I could take the blue line, the solid line, and copy the data to a CPU, and then have the CPU communicate. And so those are two different approaches for how you could communicate between two of the same GPUs. And they're going to have different costs depending on the properties of your problem. So we're looking at doing profiles on this system to see how well does everything actually work? How do we want to communicate data? And so this is a plot that's similar to the one I showed at the beginning of looking at the differences between communicating between two processes that are on the same socket versus on the same node but different sockets versus communication that has to go through the network. So the solid lines here, if I'm actually communicating between CPUs, the dotted lines are between GPUs. And we see some interesting things. So communication on socket between node or processes that share that cache, that's very cheap, which is what we would expect. However, the CPU communication on node, but on different sockets that goes through main memory, we would expect it to be cheaper than having to send across links of the network to other nodes. And it is, but only for small messages. If you look at those very large messages, that orange line is actually more expensive than the green line, which is sending through the network. It's actually more than 2 times as expensive, which means it would be cheaper for a process on node 0 to send to another node and then send that data back than it would be to just send it within its own node, which doesn't really make sense, but that is the performance we see. And then the other thing we see is these dotted lines are the cost of communicating directly between GPUs. So using those red links to go directly from GPU 0 to the network to another GPU, or going across that blue link, going directly from GPU 0 to GPU 1 across that blue line. You would think that going from GPU 0 to GPU 1 would be very, very cheap, but it's not. So if we look at the profile, the network, that green dotted line, is actually much cheaper than the on node. So it's cheaper to send from GPU 0 to some other node than it is to go right across that blue link from GPU 0 to GPU 1. Again, these performance results really don't make sense, but this is the performance we get from the computer, and that's what we have to use to optimize those applications. We also want to see, so that shows in general, communicating between CPUs is cheaper than communicating between GPUs. However, all of the data is on the GPUs, so we really care about communicating between GPUs. But there are different ways to do that. So I could communicate between two nodes, between GPUs on different nodes, by using that red link there. So going from GPU 0 across that red link to the network, across the network to another node. Or I could go across the blue link from GPU 0 onto CPU 0 and then communicate between the CPUs. So the blue line here is that on the plot is the CUDA-aware approach that's using that red link to go directly to the network. The orange line is that 3-step approach, copy to the CPU and then go across the network. So as you would expect, it's cheaper to not copy to the CPU. And that's what we hope for. That's what we want to be able to do. However, in real applications, that's not the case because we actually send quite a few messages. And if we send a large number of messages, we only have to copy data to the CPU one time, and then we can send all that data. And so it actually becomes cheaper when we're sending many messages to copy the data to the CPU, communicate between CPUs, and then copy back to a GPU, rather than going directly between GPUs, which again is not what we expected. So we have to optimize applications to take all of this into account. And then finally, one of the interesting things about these newer computers is they have a really large number of CPU cores per node. So they might have 4 GPUs per node, but they have something like 40 CPU cores per node. So there's a lot of CPU power that we could use, but applications typically don't. So typically applications are written to have one CPU core per GPU. And so we looked at if we actually use all of the available cores, would it be cheaper? And it is. So if we can communicate using all of the available CPU cores, we can actually reduce the cost of communication on these machines. So in general, we just looked at for a random operation, if we use all of this information, can we improve it? And we can. So this one's a little bit funny. I'll just look at this one. So this looks at if we send data from just the one GPU to the other GPUs using that red line, we would get this top cost, the blue line, that's the CUDA-aware. If we copy to a CPU, we get the orange line here. So it's a bit cheaper. If we copy to all of the CPUs and use each of those CPU cores that's available, we get the green and red lines. So we can improve our cost of operations and applications just by using the information we got from these models and optimizing how we do this communication. So that's a lot of what we're looking at in our research. If anyone is interested in talking more about this offline, please send me a message. But also I'm happy to answer any questions here. And just a reminder that we are hiring in case you didn't see that before. And if anyone is interested, please apply. Thank you.
Thank you so much. So from the audience, if anyone has any question, please feel free to raise your hand and mute yourself, and let's deal with your questions. Okay, why don't I ask the first question? Mm-hmm. So throughout the talk, you were saying that it's more expensive. So did I get it right that when you say it's more expensive, you're talking about the latency? Is it that, or is it something else?
Yeah, that's a great question. So yes, it's the latency or the time it takes. So it takes a really long time, which we call expensive. So just it takes more time.
Okay, so how does it affect the, like the error in distributing the data? Like if we don't do it intra and we do it, so we don't do it inter and we do it intra and then go to inter. So does it affect the error as well?
Oh, that's also a great question. So it actually does not have any effect on the solutions. So we're getting the correct results. We're just communicating them in a different way behind the scenes. So it doesn't have any effect on the error of the application. Everything is computationally exactly the same.
Oh, okay. That's awesome. Thank you so much for your answer. Anyone else with any question?
Actually, I can go next. It's not mainly a question, but I would like to follow up a little bit with Amanda. If she can discuss a little bit about the NSF, I guess it's the NSF GRFP opportunity, if I got it correctly. Like, if you can tell us like how you prepared, like what were your difficulties in terms of preparing the application, because by discussing with several NSFPDs, the common comment that I have heard is that they receive few applications from the computing field compared to other fields like biology or physics or math departments. And so you coming with a background from computer science, like, can you share with us a little bit your experience, like how you prepared your applications, what were the difficulties that you may face, and anything valuable for students that will either attend or watch the video afterwards?
Yes, absolutely. That's a great question. So I applied to the NSF GRFP fellowship when I was in the last year of undergrad. So I actually had it coming into grad school. So the quality that they expect in things like your research statement changes over time. So I was with the undergrad students who were applying. They would expect a better research statement from someone who's in their first or second year of grad school because they've probably done a bit of research. But in general, for my application, one of the big things is that they ask for broader impacts and, oh, there's another one that I'm blanking on the name.
Intellectual merit.
Yes, thank you. Intellectual merit. And so one of the big things of advice we're given is to bold broader impacts and then put a very clear, bold statement what your broader impacts are. And the same thing for intellectual merit, just to be very clear that you're meeting those guidelines, because that is a big thing that you're judged on. I'm trying to think of what else. So I had a very loose research statement because I had not really done any formal research before since I wasn't in grad school. This is a good question. Do you know, is there anything at UNM that helps prepare students for the NSF fellowship?
Unfortunately, no, it doesn't exist. And actually, this is an effort that you may be interested in joining me in that. I mean, I try to organize some workshops for at least the students in the School of Engineering, you know, that I feel familiar with some topics, but unfortunately there isn't.
Okay, yeah. So I know quite a few people who had it, so I could potentially get some statements together from people who had were accepted, so that we would at least also have some examples of people who were accepted in the program, their statements. But yes, I would be very interested in starting some kind of workshop for that.
Yeah, that would be great. That would be great. Thank you so much, Amanda.
Absolutely.
Okay, okay, I'm not muted. So any other questions? I guess our audiences are shy today. Okay, so is there anything that you would like to say before we finish today's talk, Dr. Amanda Bienz?
I don't think I have anything else other than if anyone has any questions or would like to chat about anything, please send me an email. I would love to talk to you all.
Okay, so I will be uploading this session on YouTube as well, so that if anyone would like to watch it later on, and I will be sharing the link with you as well. So I guess today's session is a bit short, and we finished before an hour. But I really enjoyed your talk today. I think that there was a lot of insights into supercomputers. So yeah, thank you so much for joining us today. I know that you have a very busy schedule, but thank you very much. So have a very good evening, and everybody have a very good evening. We will be ending the meeting today. Thank you so much. Bye-bye.
Thank you. Bye.